Time for a pop quiz.
I'm Mr. Meeseeks! Look at me! Why did you even rope me into this? Because he roped me into this! Well, him over there, he roped me into this! Well, he roped me into this!
Good morning, everyone. Welcome on in. My name is Penn Center. We're here for a joint presentation.
Hardly even a practice test.
Nice. A joint presentation between the Artin reading group and the Friedberg reading group from the Simple server. We're just waiting for the ads to finish rolling on through, and we'll be starting in about a minute and a half or so. Where is my soup? Oh, I still have to cook it. So I made the broth. I made the bone broth last night. So I just finished making the broth. I roasted some like pumpkins and squash. So it's just gonna be like a squash soup. Nothing super fancy, but there's some carrots in there. There's some carrots and ginger in there. I think it's gonna be delicious. Instante noodles. What's shitty net? Oh, bad internet tonight? Oh, that sucks. No one likes a bad internet. Alright, well, we're almost. Good morning, Martin. Hello. How are you doing? We're almost through the ad roll, so we're going to pop over into. We're actually in the. What is this? This is the Taurus mathematical server today with Ian Stuckey. Finishing up some of our algebra reading groups. So let's pop in, say hello, and see if Stuckey is ready to start.
As well as perhaps some bonus content for the linear algebra one. I don't know, Penn, if you wanted to say anything about that. But...
Oh, I was just going to come in and say hello. Hope you're doing well.
I'm doing great.
Fantastic. Yeah, so ads are rolled through. I'm here just to kind of give a little commentary and say hello to my good friend Ian Stuckey. And is there some commentary that you would like me to say?
No, not particularly. I was just kind of filling time talking about what's coming, what's gone.
Yeah, I guess the big kind of this is the big culminating kind of final discussion for the Friedberg reading group. So we just talked a little bit about inner product spaces last week, and I believe today you're giving a little you called it a commentary on the Gram Schmidt procedure, which I'm super excited to hear about.
Yeah. So yeah, just a small little bit of context to for this. So this is sort of going to be a seat of the pants lecture. There was some last minute changes that we had to make, and the short version is that at the very end of the last lecture, Mikhail discussed the Gram Schmidt procedure, or at least one way of phrasing the theorem, and so that's sort of the main object of section 6.2 of Friedberg, and so that's my primary goal, is to flesh out that discussion a little bit more. That probably will not go for our usual full 2 hours, but depending on the mood of the audience who's around and what the vibes are on this end as well, we may have a few more things that are specific to the Artin book that are going to get discussed now or later, and there could potentially be some space to do that now. But getting into a little bit more of the details here, I'd say the broad outline for today as is that, so we're talking about Gram Schmidt. I'll remind us, ooh, that's exciting, what that means in just a second. But this will take sort of two parts. The first part is going to be just a little bit about the intuition, geometric intuition. For the Gram Schmidt procedure, because there's this formula that's out there, and it's sort of imposing and maybe not super intuitive, but there's a nice idea behind it at least, and I'd like to sort of tease that out a little bit, discussing some of the other main things from this section along the way. And then we will not probably give a full proof of Gram Schmidt. It is in the book, and as Mikhail mentioned last week, the exact details are not super enlightening. But we will take this idea and we'll sort of pull it up a level. So one of the big lessons I think from the group theory chapters is that while sometimes it's very helpful to understand what specific group elements look like, right? This was a big theme in chapters 4 and 5 when we were talking about rigid motions in the plane, and we were really concerned about how like rotations interacted with reflections and so on. But often it's helpful to think a little bit more abstractly, to think about not just single objects and how they interact with each other, but in fact sort of subsets of objects, these very special subsets in the subgroup case, or in the case of groups, which is the subgroups. And so similarly for vector spaces, sometimes it's very helpful to talk about individual vectors, and Gram Schmidt is really a statement that is fully about individual vectors and the way that they behave under our new gadget, right? This inner product. But we can do sort of a similar trick and think about things at this one's level up, and that will lead us to we'll try to formulate this intuition at the level of subspaces. So that's the plan. Feel free, if there are questions, to post them in the chat. You can also raise your hand if you are in the Discord channel. But we will get started until we see one of those. So, as promised, I need to remind you what Gram Schmidt is. So I will state it in the way that Kyle wrote it. This is from last time. Which is that every finite dimensional inner product space, which is just a vector space endowed with an inner product, has an orthonormal basis. And just a one of the comments that Mikhail made is that this business about it being normal is a little bit less important than this business about it being ortho. So, as a reminder, normal in this case means, well, it's a basis, so it's in particular a collection of vectors. one, because our space is finite dimensional, it has a finite number of vectors in any basis. So normal means that if I pick a single one of these vectors, that I take the inner product with itself, and that gives me 1. Ortho means that if I take any 2 of these vectors and I inner product them with each other, then I get 0. Now this pink condition here, this normality condition, is a little bit less critical if you have an orthogonal basis, so something that only does this pairwise condition. Then you can always just divide through by so-called the norm of the vector, and to produce something, or to produce the basis that it has this normality property as well. I'm going to upgrade this statement slightly, and I'm going to do that. Well, I'm really going to point in one direction, but maybe I should say very briefly that um, this is somewhat. We don't really need the full strength of finite dimensionality here. The proof goes by induction, and so the proof really does need it. Um, but you can extend this idea to, for instance, separable Hilbert spaces. So cases where you have a countable basis. Going beyond countability, I could potentially see some problems with the proof. Genuinely, I don't know if the statement still holds in that context. For us, we're going to be focusing on the finite dimensional setting, so I won't belabor this point too much. But you can, for those of you who like to think about infinite dimensional things, this is there's something. It's not hopeless, right? But the other thing that I want to note is that, so we can upgrade this by writing an explicit algorithm. And this algorithm looks kind of intimidating. It's written directly in Friedberg. If you're impatient, you can just go look at it. But I want to mention that even though it has this sort of weird form, I think the form becomes a lot more intuitive when put in the context of a theorem that came slightly before that. Um, so, or maybe when I say intuition, this is not the geometric intuition that I'm talking about, but the sort of algebraic, uh, the algebra looks less surprising if you've internalized the following result. So this is 6.3 from Friedberg. Which says that if y, we say V is a finite dimensional inner product space, use this acronym a whole bunch. Again, I think the finite dimensionality is not super essential here, but we'll keep things simple. And we have some set of vectors. And these are not necessarily a basis or an orthonormal basis or anything, right? They're just some vectors. and I want one extra vector. But it needs to do better than just being in the vector space, sorry. It needs to be in the span of these things. Then we have an explicit formula for y, which seems like a sort of strange thing to say because so far everything is like extremely general, but we can write the y's in terms of the v's. Again, I'm putting no restrictions at all on the v's, and the only restriction on the y's that it sort of could potentially be written as a linear combination of the v's. But we can say exactly what those coefficients are. Joy from the chat asks, an inner product is just a way to combine two vectors to give an element of the field. So that's mostly correct. It is, so certainly that is a requirement for the inner product. It also has to satisfy a couple other conditions. It has to be linear in the first argument, satisfy this conjugate linearity property in the second argument, which also becomes linearity in the case of the real field. And it has to be non-degenerate in this way. The only time when a vector inner product with itself is zero is if the vector was the zero vector. So there's these technical conditions that we have to have in addition. But in particular, yes, it's definitely worth noting that this object right here is just an element of the field divided by an element of the field. So that's just a number. A question that we might get to in sort of the optional second half of today is going to be like how much all of these conditions are actually being used. And essentially for this theorem, we're using almost the full strength of the inner product. In particular, in order for this denominator to make any sense, we need to guarantee that that number is not zero. And so if you fail to have this this non-degeneracy condition, then you could potentially run into issues there. But yeah, thank you for the question. Yeah, and thanks Ben for the writing down something that's actually comprehensible. This is a pretty quick theorem to prove, if I'm remembering correctly. So let's just go do that. Okay, so because y is in the span, we know that it has to be some linear combination. Let me here. Y equals some linear combination. Some. Yeah, but it's all these sorts of formulas like the positive definiteness condition are really meant to be written written down, not meant to be spoken out loud. But I appreciate the compliment. Okay, and then what happens here is this trick, and it's really worth knowing this trick because it gets you very far in studying inner product spaces, which is to say, okay, well, if these two vectors are equal to each other, right, this y is a vector and this is a linear combination of vectors, then you can't stop me from taking the inner product of that, and I'll stop writing the hats now, with something. And by perhaps a clever choice of something, you can learn something interesting. So, there are lots of proofs that sort of look exactly like this, and this is one of them. In this case, the thing that's going to be most enlightening is we could take the inner product with ej. Right, so one of these special vectors. Sorry, I want to make a very small addendum to the theorem. Probably none of you were concerned about this anyway, but just for preciseness, these vectors can't be zero. It can't be the zero vector. For the same reason that we could potentially have those problems in the non-degenerate case, we need this denominator to make sense. Okay. And now we use our fun facts. The whole point of uh, these inner products is that they satisfy some of these nice conditions. So let's go ahead and do it. Say that, for instance, we can pull out the sum. We can pull out the coefficient. Oh, goodness gracious. Um, yes, there's a good conversation in the chat. I think that about the non-degeneracy condition, but I think that was resolved. Um, okay, I have a much more serious addendum to make to the theorem. Sorry, this is going to happen probably a couple of times this lecture. Um, I said that the VI don't have to be related to each other. That's not true. That they can just be like random vectors. Okay, so let's do better. Uh, I'm gonna need, I think, an entire extra line, and I'd rather not just sort of stick this off to the side. So let's do this properly. Um, so these need to not just be any set of vectors, but they need to be orthogonal. So we're not imposing that normality condition, but we are asking for this VI-VJ relation. And if you're quick, you may see sort of based on the calculations why we're going to want this. But otherwise, we'll just run through it. Set of vectors. And okay, now I need to remind you what y is. Y is in the span of v1. Then oh, you're right. That is a mistake on my part. That n should be okay. Thank you for that catch. And perfectly said, Joy. No worries. I'll try to keep relevant things on screen right now. Okay, so at the very, very top, it's an orthogonal set of vectors. Now we've done all of the same calculations as before, but now we're in a position to use this orthogonality condition, right? Because what we have down here is a sum of something and some VI-VJs. Well, because this is orthogonal, so yeah, is equal to. So I'm going to write down this. And the reason why this happens is because there's a whole bunch. There's v1, v2, v3 up to vk, but if I is different from j, then we know that I vj is equal to 0, and so those terms cancel. So the only term that survives this this interproducting thing that we did is the jth term. And now we're essentially done, right? We have a formula for the AJ. Solve by dividing both sides through by the norm of Bj, Bj. And that's precisely what we wanted. Because by definition, what are the AJs? They are the coefficients that we put in front of the VIs to make everything go. I'm going to pause here for just a second. Maybe I'll zoom out a little bit so that you can see the correct version of the theorem statement, as well as the proof. If folks are typing, please keep typing. I'll address that as I address those questions as I see them. But just very briefly, the where we're gonna go with this is that this theorem says what happens for y being inside of the span of the VIs. And if you're sort of very trying to be grammatical about it, then this is really the only thing that you can ask. Like you couldn't possibly ask for any other y's to work because you can't get such a linear combination if you live outside of the span. But you could try anyway, right? If you're more optimistic, you could say, well, okay, if y is inside the span, we know everything. What if y is outside the span? Can we say anything at all? And somewhat surprisingly, the answer is yes. Friedberg, by the way, notes a couple of corollaries to this, and I'll say them out loud, but I won't write them down because we're not going to use them in any essential way. The first is that if your set is not just orthogonal but is orthonormal, then you don't have to worry about these denominators. Okay, that's fairly straightforward because those denominators are all 1. Also, you can finagle this without too much work to see that this implies that if a set of vectors is orthogonal, then it necessarily has to be linearly independent. If this is your first time seeing this kind of stuff, that's probably not immediately obvious, but it's worth it. That's an exercise that I think is worth doing, perhaps without looking at Friedberg, and sort of a reminder of how the about how you prove that things are linearly independent. It's a pretty good exercise in that regard. In particular, this means that orthogonal sets of vectors can't be that big, right? You can't be bigger than the dimension of the vector space. So this theorem covers, or says what happens, maybe. It's exactly what happens when y is in the span of the eyes. Can we say anything if not? So what might we want to say? Well, one thing that we could try is um the so exactly what happens here is that y is equal to, just writing down this formula again. Now if y is not in the span of the vi's, then this equality certainly is not going to hold, because this thing would not be in the span, but the right side would be. However, it's still perfectly reasonable to ask about this object, right? That object makes complete sense, regardless of where y is. So, perhaps can we understand the relationship between y and y prime? Geometrically, this is how that story looks in broad strokes. So this is maybe our sorry. This is our span of our two vectors. Or trying to pretend that we're being general here, right? Even though we can only draw in 3 dimensions, so have to do the best with what we got. By definition, we know that this y prime is going to live inside of this plane. It's going to be somewhere over here. The y vector, if it does not exist inside the span, then it does not exist inside of this plane. And so it's going to be over here somewhere. And I've drawn this diagram very suggestively. A priori, it could be way over here. But the reason why I'm drawing it this way is because there is, in fact, a theorem which says, okay, y and y prime are different. How different are they? Maybe that's the error vector. So, proposition, and I don't think this is written out explicitly in Friedberg, although it's certainly contained in many of the proofs there. That
What about
epsilon,
me? He wrote me into this. Well, that one over there wrote me into this. Well, he wrote me
it
into
could be
this.
very large. However, we can say that epsilon is always going to be orthogonal to y prime. So there's this right angle right there. Joy asks, would y and y prime have the same dimension? Yes. So y and y prime are both vectors that are sitting inside of some vector space. Something that I haven't drawn here, and I'm a little afraid of drawing because I worry that it's going to make the rest of the picture unclear, but I'll at least put it up temporarily, is that in addition to the v1 to vk, there might be some other vectors, right? So that, and in our actual picture, there's exactly one other vector um, that fits, that makes this subspace. Let me draw the picture, and then I will attempt to say the words that I'm saying. Uh, not the not the best cube I've ever drawn in my life, but so there's this entire thing is sitting inside of some ambient vector space V, which I'm assuming is what you mean by having the same dimension. So in particular, if you think about V as being uh, Rn, so that both y and y prime have the same number of coordinates. But we are choosing to not use this third vector. So um, we're restricting our attention to just the this black subspace here. That's spanned. Oops, black. That's spanned by our two orthogonal vectors of choice. If you prefer to just make things very concrete, you could think about v1 and v2 as being like, and then v3 as being the third inner basis vector. So that all of the action with the vi's and the y prime in particular is contained in the xy plane, but that doesn't prevent us from thinking about this this xy plane as sitting inside of a three-dimensional subspace. Change that n to a 3 so that the verbiage is coherent. So the subspace is an inner product space part of a larger vector space, which is why our y, in which our y is correct, which is why the base of our subspace can't represent y. Base of our subspace can't represent y. That's correct. Yes. I will say the inner product here, the inner product on R3, or the dot product on R3, is defined over the entire thing. It makes perfect sense to ask, in particular, like this numerator here. I have to be able to make sense of that numerator. However, there is, I think that your idea is correct, right? There's um, a big ambient space which has an inner product. There's a subspace that has the same inner product, but doesn't use all of the vectors. And y prime is contained, or excuse me, y is contained in the big space, but not the little space. Yeah. Yeah, thank you for these questions, Joy. So this picture that we have here is really the core idea of Gram Schmidt. That if you start off with, yeah, so maybe I'll write something specific. The core idea of Gram Schmidt is that given an almost orthonormal basis, so there's one vector that's sort of screwed up, but the rest would be orthonormal. Um, then we can replace um, the screwed up vector, so the bad y vector, by this error vector. And then we're going to cover, we're going to span the same space that we did with the y vector. Again, you got to prove that, but not too bad. And it's not necessarily orthonormal, right? But it's at least orthogonal, because well, again, this takes a little bit of proving, right? Is orthogonal to vi. All right. Let me again zoom out slightly so that we've got the full picture. And this brings us to the conclusion of part one of the outline that I was talking about earlier. Um, this is somehow the geometric intuition of Gram Schmidt that we can replace these sort of bad vectors um, iteratively, right? So at first, there's just you sort of forget that all of the bad vectors exist except for one of them, and then you replace that bad vector with a good vector, and then you do it again, and then you do it again, and then you do it again, and because the space is finite dimensional, eventually you stop. Actually, you've made all of the vectors good. Along the way, you don't change any of the subspaces that you construct. So for those of you who have sort of highfalutin geometric interests, this is a basis is equivalent to a flag of vector spaces. Well, more or less equivalent to a flag of vector spaces, and you don't change the flag when you do this. This Gram Schmidt procedure. And also, as was commented at the very end, there's a notion of orientation of vector spaces. And so if that's something that's familiar, this procedure also does not change the orientation. So it's quite good in a lot of ways. Use the Gram Schmidt procedure on politicians. Okay. I'm vibing. All right. So I guess that when I was saying something earlier about um, this business about the Gram Schmidt says something about individual vectors. Um, maybe this is what I mean. Like we're sort of we have this big set of vectors, this that we're trying to make orthogonal, and so we sort of one at a time. Right, each individual vector we make it into something good. Can we perhaps do this all at once? Can we talk about something a little bit more refined than just this single vector epsilon? Is there a natural place where that vector epsilon lives, right? It certainly lives inside of the entire vector space, but perhaps a subspace that we could choose it from. And meditating on this for a while, which we will not do here, we'll skip the meditation, um, but we'll leave you to, or certainly historically led people to the concept of um, the orthogonal complement. Of A. And it's been a while since I've written this down. Remember, this means a finite dimensional inner product space. Again, finite dimensional is not super important, but um, you know what? Actually, finite dimensional is not important, and for some of the examples that Friedberg uses, it's actually really significant that we can do this construction in infinite dimensions. So let me just this once. Um, then yes, as Ben Center says, the orthogonal complement of W is denoted by W with this upside down T, usually called W perp. And so this consists of all vectors that live, maybe I shouldn't call it W, consists of all vectors U in the big vector space, so that um, for all vectors W inside of the subspace, we have that U and W are orthogonal. So I don't believe that this is precisely the definition that Friedberg gives, because there's a trick, and I really would encourage you to just think about this as a trick. W here does not actually need to be a subspace. Okay. We can improve this definition. I'm going to put this in scare quotes. You can improve this by saying that S is a subset. So you can talk about the orthogonal complement of just like a random collection of vectors. However, there's a meaningful sense in which orthogonal complements really want to act on subspaces. They really prefer those sets of vectors. Um, and so I don't even think that Friedberg gives this a ton of airtime. But let me just say that if you use this improved definition, supposedly improved definition, then the orthogonal complement of a set is equal to the orthogonal complement of its span under the non-improved definition or the improved definition. Um, so you don't gain anything interesting by going uh, by getting rid of subsets that are not subspaces, right? Every orthogonal complement of a subset was already the orthogonal complement of a subspace. Space being space spanned by. It can be kind of nice to just not have to write down the word span every so often, right? And just write down S perp, but I think that conceptually it's a little bit cleaner. That is a Ian Stuckey opinion. Um, a fair question is what is complementary about this uh, complement? Perhaps if this had been invented in on a later date, it would have been called the orthogonal dual, because one of the most significant facts about the orthogonal complement is that for any subspace W in V. Again, V being an inner product space. We have the following very sort of needlessly concise formula, which is that the vector space, the entire vector space is the direct sum of the original subspace W together with its orthogonal complement. Intuitively, what this means is that the orthogonal complement contains everything essential that the subspace does not. Less intuitively, but better for proofs, this statement splits into two pieces. On one hand, we need to show that W intersect with its orthogonal complement is 0. It's the 0 subspace. So there is essentially nothing in common between these two vector spaces. Between these two subspaces. Well, every pair of subspaces has the 0 vector in common, but they don't share anything else. And also that to that, okay, and I'll write sort of, again, the sort of too nice version of sentence, which is that if you remove the circle, so somehow this pink statement accounts for the circle around the plus. The plus itself means that every vector V in V can be written as V equals W plus U for some W in W and U in W perp. And this is a theorem. Which theorem? Theorem 6.6 from Friedberg. And what I'd like to do just to finish off, maybe I'll say one more thing afterwards, but to finish off this Friedberg section of the lecture is just to give a proof of this. I think this one is also not too bad. So we need to prove two things, right? We need to prove the pink bit and the orange bit. Well, the pink bit turns out to be not too bad. So if we have a vector v, that's inside of this union, so it is both in W and its orthogonal complement. Then, because it's in the orthogonal complement, we can take its inner product with anything inside of W and get 0. But because it's also in W, then we can choose the thing that we inner producted it with to be itself. And to go back to this discussion that Joy was bringing us to earlier, this is a big problem, right? The only way that this can happen is if V is by non-degeneracy. This implies that V is C prime. Yeah, I think so too. This non-degeneracy condition, it sort of seems esoteric when you just say it abstractly, but it turns out to be very, very useful. Um, okay. I'm just now remembering this proof is somewhat annoying. Um, so I think I'm going to um it's annoying, but it is just kind of a calculation. Um, Perhaps along the way we're going to prove this proposition that I said was an exercise though. I'm just checking that real quick. Yes, that's the case. So perhaps I'll just use that proposition instead. Um, so uh, by our exercise proposition, which again is just kind of a calculation. Um, um, we can write okay, this is bad grammar. Let's try this sentence again. Uh, okay. You can't stop me uh, from writing uh, W equals this V prime thing from before. That is, choose a basis, a uh, orthogonal basis. We can even say an orthonormal basis of W, which is always possible by Gram Schmidt. Let's give that basis a name. We'll do V1. I'm regretting some of my notational choices. Then, um, in fact, I'm really regretting my notational choices enough that I'm going to go back on it. I'm going to call this thing that I called V before. I'm going to call that Y, just to align a little better with the notation from that I'm stealing from up above. So nothing has changed. I've just called the vector that I'm trying to decompose in this way by a different letter. Then oh, we can try. That stopped me from trying. W is equal to the sum of I over vi, which I guess we don't technically need this because I said it was orthonormal, but just to keep things here. Okay, so I'll make this comment because it's normal. That is 1. Okay, and that means we know by the unproven proposition above which again, I've said this like 3 times already, but that proposition is a calculation. then we know that this W and Y minus W are orthogonal. In other words, W or Y minus W, or yeah, Y minus W is in W perp. No, this is not quite right either. So what is not right about this is, so certainly you can't stop me from getting this far. That's true, but this does not follow from that statement, right? Um, right. I'm going to, for the sake of for the sake of sanity and not rewriting things too many times, I'm going to cut off the last sentence here and say, well, I never actually was going to prove it. I was just going to sketch a proof for you. Um, oh, so this, we can try this. So now is actually going to say this works. Um, so I'll say maybe turns out one can check that uh, that W equals this and yields Y minus W. So what do you have to check? That this is actually in the orthogonal complement. In other words, that Y minus W if Vi is 0. Because if it's orthogonal to all of the all of the basis elements, then it's going to be orthogonal to any linear combination of the basis elements. Yeah, exactly. This is whiteboard math, right? All right. So this is normally about the place where we would take a quick break. I think let's do that, but let's make it quite quick. We'll come back. Perhaps so it's 6 past the hour, and we'll come back at 10 past the hour. So just a few minutes to stand up and stretch. I don't want to make a big commentary, but one thing that I would like to do is to just define the notion of a bilinear form, and to sort of talk about the things that we've talked about here in terms of that definition. This is, again, Artin specific material, so if you are here for the Friedberg linear algebra group, you are free to go. But we will at some point be talking about these slightly more general objects for chapter 7 of Artin, so I want to start introducing them now. In any case, I don't want to eat too much more of our break time. See you very soon.
And for those of you on Twitch, I'm just going to use this opportunity to run the ad break. So we'll see you back here in a few minutes.
Time for a pop quiz. Hardly even a practice test.
Okay, it looks like the Twitch is back. I am back, so let's get schmoving on the second half here. Joy has a comment in the chat in which you're stealing my thunder. But yes, so we're going to begin by defining bilinear form, which is exactly what Joy says. Goodness gracious. Can we... Yes, please. Back to content. No. All right. So I'm going to contextualize it slightly, but if you're anxious to see the definition, it is currently in the Discord chat. So recall that inner product is a map from the field cross the field to, or nope, not exactly, from a vector space cross a vector space. So you take in two vector space arguments, two vectors, and you spit out a field element, satisfying our couple of rules. And I'm going to make sure that I'm using Friedberg's characterization here. So satisfying four axioms. That x plus y. I don't need to be so bound to the notation here, but just to prevent myself from making too many mistakes. Okay, so this is true for vectors x, y, and z. Also needs to satisfy linearity in the first argument. It needs to satisfy linearity, or excuse me, conjugate symmetry. So if you conjugate it, then how? Okay, I'm gonna be have a weirdly strong opinion here and say that it should be this. If the inner product is backwards from what you want it to be, then that's fine, but you do have to pay the price of conjugating that field element. And then if x is not 0, not the 0 vector, then is 0. And I'm going to split this into two axioms. Say that what do I want? Yeah, I'm gonna rephrase this one very slightly, actually, to say that xy is greater than or equal to 0, and xy equals 0 if and only if x is equal to y. That's also not true. What are we talking about here? What are we talking about? Let's try one more time. I'd like to say things that are more or less accurate. Only if x is the 0 vector. Okay, that's better. So Friedberg sort of only cares about this half. Yes. Okay, so some commentary on this definition. So these first two things here say that this is a form that's linear in the first argument. Ah. And it's not terribly difficult to just sort of like reverse everything for the second argument and conjugate everything, and to see that it's conjugate linear in the second. So, in other words, let's say conj linear in the second. Okay, so I said this, but in particular, what this means, Ivan. So here's the thing: we wish that were true, but it's not quite true. Oh, sorry. No, that is true. That one is true. The one that's not true is the multiplication, which is that. Right. So c or x ey is equal to not c times xy, but the conjugate of c times xy. We are working only over vector spaces, although certainly you can define bilinear forms on general modules, yes. Yes. Although we haven't actually defined a bilinear form yet. So far, we're entirely in the inner product case. So not only are we only looking at vector spaces, but we're also only looking at vector spaces over, let's just say the real numbers or the complex numbers. You could be a little bit more general than this, but not that much. You have to take the conjugate and swap the arguments to use linearity in the first argument. Exactly, Joy. So this business about being linear in the first argument and conjugate linear in the second argument is sometimes, I think this is sort of a cheeky name. I don't know if this sort of thing ever shows up in any other context, but people have chosen to name this. This makes the inner product into so-called a sesquilinear form. So what the heck is up with this name? Well, this prefix sesqui, um, I think most people in this chat are probably familiar with, mono means one, bi means two. Well, it turns out there's this incredibly specific thing that means 1.5. This is not a math thing. This is just like Latin. um, and so somebody thought that this was very funny and stole this terminology. So the is 1.5 linears, right? Um, Now you see this, and sort of your natural inclination is to say, well, okay, could we just not, right? Could we just not deal with this conjugate linearity? Um, and the answer is yes. So a bilinear form. Um, uh, which I'm going to denote with parentheses, and this is sort of unfortunate because parentheses do a lot. But in math they do a lot, but this is pretty standard, is to use parentheses for a bilinear form. Taking in two vectors and spitting out a field element. Satisfies 1, 2, and what you wanted 3 to be, or excuse me, well, maybe I'll say what you wanted from 3, which is that, actually, no, we really need some more than this. Prime, where 1 prime and 2 prime are what you think they are. This is x, y plus z, xy plus xz. And I'm screwing up my parentheses. And this is that y is equal to c. So written in this language, one thing that I think Mikhail mentioned, but I'll say again, is that if your field is the real numbers, then you don't have to worry about this sesquilinearity business, right? The conjugate of a real number is itself. And so an inner product is in particular a bilinear form. Let's focus on that case for a second because it's going to point out some things that were that I'm going to be interested in going forward. Which is primarily that, like, okay, over the real numbers, a bilinear form, excuse me, an inner product over the real numbers is a bilinear form that satisfies 2 extra conditions, right? It satisfies this business about the conjugate, or excuse me, forgetting about conjugates, the form is symmetric. if xy is equal to yx. No, I think this is the definition we're going to take. So you can ask about not just all bilinear forms, but all symmetric bilinear forms. But even then, it's an inner product is special among the symmetric bilinear forms because it also satisfies this non-degeneracy condition. Well, it satisfies the non-degeneracy condition, but it does so in sort of two separate ways, right? Which is why I took that moment to separate out these two bits from the theorem. A priori, there's no reason why a bilinear form should have to be positive, right? I probably should have come with a specific example of this. And I wheeled one right on the spot. Sure. So a sort of silly example of a bilinear form. Okay, you know what? I say silly, but maybe not so silly. Uh, is take V to be just the plane. We know that remember that here the usual dot product is x1, y1 plus x2, y2. But we can make a bilinear form. I mean, it has lots of bilinear forms, but one of them could be just take this definition, write out the left-hand side of this, take the definition, but stick a minus sign in there instead of a. Can't stop me from doing this. It's certainly linear in both arguments. It's not symmetric. No, it is. It is in fact even symmetric. Because if you replace the x and the y, then you're just changing.
Prepare to be iterated.
But it fails the last condition because if you look at the vector 0, 1 with itself, right, those are zeros up top, then this is 0 times 0 minus 1 times 1, which is negative 1. So this is a symmetric bilinear form that that fails this symmetry condition. Or excuse me, no, that succeeds on the symmetry condition, but fails on this non-degeneracy condition. It also fails on the second half of this. We can see this by looking at the vector 1, 1. That's going to be 1 minus 1, which is 0. So this is a non-zero vector whose inner product, quote unquote, okay, its bilinear form with itself is 0. And so these are the sort of pathologies that working with an inner product allows you to avoid. How much terminology do I want to introduce here? I've already talked about non-degeneracy. Um, Let me perhaps call this. So let me just write down sort of a careful definition. That is what it means to be non-degenerate, and this other side is positive. And I guess the usual word here is positive semi-definite. If you are both positive semi-definite and non-degenerate, then you are positive definite. So this semi is allowing for the possibility that occasionally you might be zero. Thanks, Ratel, for stopping by. Yes, and as Kaler Cohn is noting in the Twitch chat, this form that I threw out here is not random at all. It has some physical meaning, or at least it's some toy model for something with physical meaning. But I don't know any physics, so I'm going to not say too much more than that. The last thing that I want to do, and this is hopefully just going to take a couple of minutes, and then I'm going to open it up to questions. Seems like there might be some rummaging around in the chat right now. Is I want to go through, just sort of skim through what we did in the first half of the lecture, and I want to point out which properties are getting sort of used at any given time. I think that is all I want to do. Yes. So scroll back. Okay, so we've got Gram Schmidt, and we'll come back to Gram Schmidt because we sort of have a loose sketch of what that's supposed to look like. Now I mentioned this at the time, but let's start with this theorem 6.3. Since we have a full proof of it, we can sort of look carefully. We've claimed that we are using an inner product. Are we really? Are we really using the inner product? Yes, Ivan. I didn't introduce the notion of anti-symmetric forms because we're not going to say very much about them for quite a while, but that's true. That's something else that you can do, and something else that Artin does in a very sort of engages with in a very serious way. So hold on to that idea for another month or so. Um, okay. So at this step right here in the main calculation step, I would argue, we used the fact that it was our form was linear in the first argument. We actually don't use the fact that anything is going on at all in the second argument, which is kind of funny. I think I don't use a lot of green throughout here, so I'll maybe make that my color here. And then at this very last step, right? So this formula is true for any bilinear form, indeed any linear form that's even just linear in the first argument, as long as you have some sort of normality condition, right? Sort of orthogonality condition. And I'll say a few things about that in a second. But this last, going from this line to this line, we have to use the fact that Vj is non-zero. In order to solve this equation for the Aj, we need to use our positive definiteness, or at least I guess we're really using the non-degeneracy condition here. Careful. What are the only thing that we need the non-degeneracy for is to show that these VJs, inner product with themselves, are non-zero. So perhaps need is a strong word. In principle, you could sort of carefully choose your VJs, so that even if your form was degenerate, you still could sort of complete this procedure. However, this gets very tricky because in order to do this step, right, this step right here, we need this fact. So we're now starting to ask like quite a few things of our VJs. If our form is non-degenerate, we're really asking the VJs to be even more special than just what they were before. Just this orthogonality condition, because we also need them to be non-zero with themselves. One sort of way that you can skirt this, and Artin does this in fact, is that you can ask, perhaps instead of this being an inner product, V having an inner product, say it has a linear form, if we at least know that it's non-degenerate. On this subspace. So perhaps, right? Perhaps we have our example where we've got the where we've got this degenerate form, but note that this is an inner product on vectors where the second coordinate is 0. Kind of silly, but you can create more exotic examples. This is in some sense cheating, right? Not because this is such an outlandish condition, but because, well, what we're really then doing is we're just using the same theorem, but we are applying it to a different vector space. Instead of the entirety of V, we're applying it to just this subspace where our form happens to be an inner product, actually. So I would describe the inner product condition here in this theorem as being essential. What does degenerate mean for a bilinear form? It means that it's not non-degenerate. So that means that there is some non-zero vector. Right, so there's some x such that this implication fails. So there's some non-zero vector so that its form with itself is nonetheless 0. I see where this question is coming from. And perhaps I'm saying something slightly non-standard. All right, continuing on. Well, in order to write down this y prime, right, we again need to know that these things down here are non-zero. And so we're again using at least the non-degeneracy. And in fact, when one goes through the proof of this proposition, or when one goes through the proof of Gram Schmidt, we're going to use all of the other conditions as well. Again, we can do this sort of cheating thing. We can say, we don't need the entire space to have an inner product. We only need a subspace that we care about to have an inner product. But then only that subspace is going to have the orthonormal basis. We could potentially have problems with extending that orthonormal basis to the part of the space that does not have the inner product, the full strength of the inner product. Okay. Now we get to here. So this definition of the orthogonal complement is actually completely sensible for any bilinear form. A funny thing about doing that is that in cases when we do not have such a strong positivity condition, this orthogonal complement can look very strange. So for instance, going back to our favorite example, this pink line here shows that the orthogonal complement W then technically we've only shown one containment here, but one can prove, in fact, that the orthogonal complement is itself. Very strange. And in particular, this means that our theorem from before of saying that everything that is some sort of everything essential that is not inside of the subspace is going to be contained in the orthogonal complement is not going to hold, right? In fact, nothing for this example that is not inside of W is contained inside of W perp. So even though the definition only requires a bilinear form, and one could argue it doesn't even really require that, just an arbitrary function with two vector space arguments, or two vector arguments. But certainly it works for any bilinear form. This theorem is going to fail. Need a non-degeneracy condition. The very last thing that I want to say, actually the very last thing that I want to say, is that Artin gives a slightly more precise statement here, which is that if, which is like actually a kind of converse to this statement, this pink half fails precisely if our form is not non-degenerate. So, so the thing that one can say, and I could find it in Artin, but just for the sake of time, let's not. Says that v oh, this is an Artin version of the statement. Is that v is equal to w plus w perp if and only if our bilinear form is an inner product and this time it doesn't have to be an inner product on the entire space. It can just be an inner product on the subspace, and this time that's actually significant. Because now we're not cheating in some meaningful sense, right? Even though before we claimed that sort of worrying about this subspace condition was cheating because we could just pretend that it was the same theorem but restrict V to just be the subspace that we cared about. But here we can't do that because if we change the V to be W, then you fundamentally changed what this equation is saying. Then it becomes very boring that you're just saying that W is equal to essentially itself, right? But the content of sort of Artin's version of this claim is that even if you only have the non-degeneracy on this small piece of your vector space, that still is enough to give you this orthogonal decomposition into W and W perp, which is kind of cool. I said that was the last thing I was going to say. I meant it. Thank you so much for coming out. And we're going to have a speaker next week, same time, same station. That is going to be Sheaf Cohomology, is the username, better known on this server as Driz. And they're going to be continuing with our with the discussion of Friedberg, going through that in specific, pulling Artin along the way. And I should know what those topics are, but I don't. We're moving toward the spectrum.
Awesome. Thanks so much, Suki. We'll, I guess, open the floor in case anyone has some last minute thoughts or questions or concerns. And I apologize if you're hearing a very excited dog running around the house. So Stuki, I have a question for you. So Driz will be here with us next week. So should we plan to meet again at roughly the same time next Sunday?
Yes.
Okay, perfect. So not seeing anything happening over on the Twitch side, I'm going to fire Twitch down. I know, dog's not here, sorry.
Actually, before, while we still have the Twitch audience, let me say so this is the last talk for February. So Driz is going to be our first talk in March. Driz is currently our only scheduled talk in March. We are looking for folks to finish off to, I believe, actually present the spectral theorem chapter from Friedberg, as well as to look a little bit more into the bilinear form, this anti-symmetric stuff that Holly was getting at, as well as getting into these classical groups in Chapter 8. If that all sounds interesting to you, then I would encourage you to either just DM me, and we can work things out, but the best way to let us know your interest is to fill out the presenter's form. I will put that in, I put that in the Twitch chat too, I guess.
If you put it in the Discord chat, I can copy and paste it into the Twitch chat if you don't have it open.
Definitely. And we will do that now. Text, is that what I want? Well, that is what I want. The presenter's form is right here.
Perfect. Let's see, let's copy that. We'll throw that over into Twitch chat. So if anyone is interested in helping out with some presentations up and coming, feel free to fill out the form. It's been your boy Will Smith signing out. See you later, GDS Fish. All right, thanks again, Sticky. I guess, see you same time, same place next week.
Absolutely.
And as always, we will get this VOD up and posted onto the Simple Group YouTube channel. We'll be doing that over the next couple days, and I will get that information out to Stuki. And then I assume that you'll also throw up your notes for anyone that wants to review as well, right?
That would be a good idea, yes.
Fantastic. So we will organize all of those things in the background for you over the next day or two. Okay, take care, everyone. Bye.
Bye.